everybody. Welcome back to Measure Theoretic Probability. In this video, we're going to talk about the limit of a sequence of sets. So far, we've talked about sets A1, A2, A3, etc., coming out of a sigma field from a measurable space, such as an omega and an F. And the numbers on the sets, the labels, the subscripts, have kind of been meaningless. It's just a way to show us more how many sets we had than anything else, because we've been unioning them and intersecting them, and the order makes no difference at all. But what if the ordering of these sets was important? So A1 was definitely the first set, and A2 was the second set, and A3 was the third set, and so on. Can we talk about these sets having a limit? I'm going to write the limit as n goes to infinity of an. This is what we want to define in this video. I hope it's another set. And sometimes often I'll use the notation the limit over n of an, and you can assume that n is going to infinity. It always does in this course. I can imagine a sequence of sets like this that appear to be approaching something, but that's only because I'm thinking of these sets in terms of a metric space. A metric space is a space that has a sense of distance. So if you're dealing with the plane R2 and you have literally circular sets, these are not Venn diagrams, and they're getting smaller and spiraling into something, maybe these sets are approaching a set in some sense that you or I could be comfortable with. But for us, we've got pretty generic sets at times, like sets of heads, 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 tails. And what would it mean to have a limit in this case? So first, I want to start with the case that seems kind of maybe clear. Let's take omega to be the real line, so the one-dimensional reals. And I'm going to define the sets an to be the closed interval from 0 up to 1 minus 1 over n plus 1. So if we write out a few of these, a1 is 0 to 1/2, a2 is 0 to 2/3, a3 is 0 to 3/4, etc. And they appear to be approaching something. One thing you'll notice is that there's containment. The first set is completely contained in the second set, is completely contained in the third set, and we appear to be approaching the interval from 0 to 1. Because the right endpoint never quite makes it in, the right endpoint for an is always 1 minus a tiny, tiny number as n gets large, I don't think we're ever going to see the actual 1. So I'm going to guess that the limit of this sequence of sets is the interval closed 0 to open 1. And I'm going to put some quotes around this because this is just my intuitive feeling about this. I've yet to define the limit. But again, what are we going to do for more general spaces, or even in R for more general weird sets that are not so nicely contained like this? This is what we want to define in this video. To get started, I want to go back to a sequence of numbers. Now, I debated for quite a while whether or not I should do this. To define a limit of a sequence of sets, we're going to go through a limit inferior and a limit superior, a lim_inf and a lim_sup. If you haven't heard of those, that's absolutely fine. We're going to define them here. But I know some of you have probably heard of these things in terms of sequences of numbers. Now, the debate that raged with me is that I don't think the analogy between sequences of numbers and sequences of sets is all that great. So maybe I shouldn't include this part, but I'm going to do it. Let's let an be a sequence of real numbers. I want to define what is known as a limit superior or limit supremum, or simply lim_sup of the sequence. And again, n is going to infinity, and I could put the right arrow infinity here. So I'm going to plot a sequence, and I'm going to have an x-axis, a y-axis. These tick marks are 1, 2, 3, so the indices. The dots are A1, A2, A3, and these curves are just here as a visual aid. I want it to sort of look like the points are maybe piling up around these curves. And if the curves get closer together, then the points might be all piling up into one thing, a limit. If you're taking like freshman calculus, you probably are defining limits in terms of things that you're getting close to with a little less rigor than using a lim_sup or a lim_inf, which is usually something that is presented to you in an analysis course. Let's talk about the lim_sup, the limit superior or limit supremum. Here is A1, here is A2, here is A3, here is A4, etc. I want you to consider the supremum, which is essentially the maximum, of all of the A's. In this graph, it appears to be right here. Now I want you to knock out the first A in the sequence and consider the supremum or quote unquote maximum of the rest of the A's. And that still appears to be right here. Now I want you to knock out the first and second and consider the supremum or maximum of the remaining A's, and that one appears to be right here. As we do this, we're going to knock out more values and recompute the supremum or maximum, and that can never go up, because if you have a set of numbers and you have a largest one, at any point in time, you could take that out, in which case the maximum is now the second largest one, so it'll have gone down, or maybe you didn't take out the max, in which case the max is still the same. So we get kind of a decreasing sequence. Really, the technical term is non-increasing because the sequence could stay constant for a while. And because it is non-increasing, it has to be approaching something, even if that something is minus infinity. So the Limsup, I'm going to look at the maximum or supremum again of all of these, and then remove one and all of these, and then remove one and then all of these. And I'm going to form a limit out of that new sequence. So this is defined as the limit as n goes to infinity of the supremum of the AM, where m is greater than or equal to n. So when n is 1, this is all of the A's. When n is 2, this is A2 out through all of the A's. When n is 3, this is the sequence A3, A4, A5, etc. And so we're going to be souping or maxing each of those subsequences and taking the limit. And this is how you define a Limsup. Because this is non-increasing, the sequence is non-increasing, we can also get the limit by looking at the minimum of the sequence, or the infimum. So another way to define a Limsup is going to be the infimum over all n greater than or equal to 1 of the supremum over all m greater than or equal to n of am. The second thing we need to define is a Liminf, which stands for limit inferior or limit infimum, and most people just say Liminf. So I think you know what's coming here. I'm going to look at this entire sequence, A1, A2, A3, and I'm going to look at the minimum number, or the infimum, from that set. And that appears to be, I don't know what's going on the right side off the screen here, but that appears to be this number. And now I'm going to remove the first number in this sequence. I'm going to remove A1 and look at the minimum or infimum of what's left. And that again appears to be this number. I'm now going to remove A1 and A2 and look at the minimum or infimum of what's left. And that still appears to be this number. And I'm going to remove the third one, and the minimum or infimum of what's left still appears to be this number. But as we keep chopping off the beginning parts of this sequence, we'll eventually pass this value, and the minimum will go up, right? Because we have a minimum of a bunch of elements in a set, and if you take things out, your minimum is not going to get lower. You either took out the minimum, in which case the next highest value becomes the minimum, or you didn't take out the minimum, in which case the minimum stays the same. We define the Liminf of the sequence of numbers as the limit as n goes to infinity of the infimum over all m greater than or equal to n of a sub m. So we're looking at the infimum of all the am for m greater than or equal to 1, and then the infimum for all m greater than or equal to 2, and then for m greater than or equal to 3, etc. And we're forming a new sequence that we're taking the limit of. Because this sequence is non-decreasing, it's kind of going up or maybe staying flat. The limit will not only exist, but it will be the largest value in this sequence. So just like we did with the Limsup, we can define a Liminf as a supremum over all n greater than or equal to 1 of an infimum over all m greater than or equal to n of am. I drew this funnel part to sort of have something for this upper sequence and lower sequence to cluster around and maybe approach, if you imagine the funnels leveling off way in the future. But if the funnels not only level off, but come close to each other, then the Limsup and the Liminf are coming close to each other. And that means everything's coming close. We say that if the Limsup is equal to the Liminf of a sequence, we call the common value the limit, and we write the limit of the ANs, which again is going to be the common value of the Limsup and the Liminf. If the Limsup and Liminf are not equal, then we say the limit does not exist. So this is not what we need today. It was just a precursor to talking about limits in terms of Liminfs and Limsups of sequences of sets. You may or may not have seen this already, but now you've definitely seen this with sequences of numbers. So let's go on to the sets. Before defining the Limsup and Liminf and therefore limit of a sequence of sets, I want to look at some more examples that are more general than the intervals we had already looked at. So suppose we have a sequence of sets, and suppose that it is a decreasing sequence in the sense that the set A1 contains A2 and that contains A3 and so on. So a picture might be like, here's A1, here's A2, here's A3. And in this picture, it might look like they're shrinking to the empty set, but that's not necessarily true. They could be wrapping around some set here. Like they could be approaching, but never quite hitting or actually hitting the boundary of a set down here without becoming the empty set. In this case, how would you define the limit of this sequence of sets? We appear to be approaching a set that's in the middle there that you can get from these sets by intersecting them. So in other words, the limit, and I'm going to put this in quotes because it's not a formal definition, of the ANs appears to be the set A, where A is defined to be the intersection of all the sets. This seems to make sense in the case of a decreasing sequence of sets. When this happens, and when I formally have defined this limit, we'll write AN with this kind of southeast arrow. The ANs go down to A means that you have a decreasing sequence of sets and they're decreasing to the intersection. You know, there's another direction here. Suppose that the sets are getting larger. So A1 is contained in A2, is contained in A3, is contained in A4. And I say larger, but I don't necessarily have a metric or distance here, but I do have containment, which makes sense for sets like heads, 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 and heads, heads, tails. You can have a set contained in another set. So the picture would look like maybe this is A1, A2, A3. And while this may look like it's blowing up to the whole space, just like we had in the previous slide, this could be approaching some boundary out here where these sets get closer and closer and closer. And in this case, I would like to define the limit. I'm going to put it in quotes because I have yet to actually define it. This is, again, intuition, but I would define the limit of this sequence as the union. That'll get you out to that ultimately largest set. We would write that the ANs increase. So we'd use this northeast arrow, increase to the set A, where A is the union of the ANs. So if you see this alone, like at the beginning of a proof, like suppose AN increases to A, that means that the ANs must be increasing contained sets like we have here, and the A must be the union of the ANs. Again, though, quotes, not sure how we're defining this limit, but that seems to make sense. Feels right to me. Now I'd like us to consider any sequence of sets, A1, A2, A3, on up. They don't have to be increasing. They don't have to be decreasing. They could be disjoint. They could have some overlap. General sets from, I'm not really using it right now, but it's going to be from a sigma field in a measurable space. So these sets may not be increasing or decreasing or anything like that. But if you look at the union of all of them, and then you look at the union of all of them after taking the first one out, looks kind of familiar, and then the union of all of them after taking the first two out, etc., you're taking a union of less and less things. And so this is a decreasing sequence of sets in the sense that this set contains this set, and this set contains this set, and so on. So we can, in our intuitive sense, talk about a limit of this decreasing sequence. It should be approaching the intersection of the sequence. So I would write that like this: the limit as n goes to infinity of the union as m goes from n to infinity of the am appears to be the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of am. That feels pretty good as well. We didn't start with anything increasing or decreasing, but we first formed a particular sequence of sets that happened to be decreasing in this case. We can go the other way And instead of looking at partial unions, we can look at partial intersections. So first I want to intersect all the A's, and then I want to remove the first one and intersect what's left. Then I want to remove the first one and the second one and intersect what's left. And the intersections can only be getting bigger, right? Because if you intersect a lot of sets, you potentially have a really small piece, not a lot in common with all of them. But the less sets you have, the more chance you have of stuff being in common. So the intersection is increasing, or at least not decreasing. And we already have an intuition about the limits of an increasing sequence of sets. So we might say that the limit as n goes to infinity of this sequence. So that means the intersection as m goes from n to infinity. So when we run the limit, n is 1, n is 2, n is 3, and we get these partial intersections, this is an increasing sequence of sets. So it's that picture where the circle's built outward, and the limit, I would say, is the union of all of them. So this double, union intersection thing and the intersection union thing on the previous slide are how we define the lim, inf, and lim sup of sequences of sets. So these are just definitions. There's no how did you get that or why is that true? The definition of the limit supremum or limit superior of a sequence of sets an is going to be the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of the set am, and the lim inf is going to be the union as n goes from 1 to infinity of the intersection as m goes from n to infinity of the am. And because this is a decreasing collection of sets as you move n, and this is increasing, we have those nice intuitive ideas about what the limits would be. They would be the intersection and union as written here. Again, this is just our definition of the lim sup and the lim inf of sequences of sets. Note that the lim sup and the lim inf is just another set. It comes from set operations, intersecting and unioning things. These are sets. And I claim that the lim inf set is contained in the lim sup set. It could be the same set, and I think that's going to be how we define a limit. But first, let's prove this claim. So to prove it, I'm going to take an element out of the supposedly smaller set. I'm going to take, this is my little omega, from the lim inf, which means it comes from the union of the intersection of the AMs. Now, if it comes from a union as n goes from 1 to infinity of sets like this, that means that it's in at least one of these sets for at least one n. I'm going to fix that n, make it really special here, and suppose that it's n equals this capital N, because our lowercase n is an index that keeps running around and going to infinity. So this capital N is like a fixed value where we could find this little omega in this intersection. If little omega is in this intersection, then it's in a sub capital N, a sub capital N plus 1, a sub capital N plus 2. It has to be in all of them because it's in the intersection. And that means that omega is going to be in the union of the AMs, no matter where you start that union. Because as you look at the A's, eventually out in the tail of the sequence of sets, every one of them is going to contain the omega. So if you union from anything to infinity, that's going to contain the omega. In other words, again, omega is in the set, the union from m equals n to infinity of am for all n greater than or equal to 1. If it's in all of them, though, over n, it's in the intersection. If omega is in the intersection of the union of the AMs, that's how we define the lim sup. So I started up here with an omega in the lim inf set, and I showed that it's in the lim sup set, and that's how we show that the lim inf set is contained in the lim sup set. And that containment could be an equality, but we have shown that anything from the lim inf must be in the lim sup. I think you know how I'm going to define the limit of the sets. If the lim inf of a sequence of sets is equal to the lim sup, then we'll call the common value the limit of the sequence of the an. So we'll define the limit as n goes to infinity, or maybe I won't write the arrow infinity, of the an as that common value. So now we have a formal mathematical definition for the limit of a sequence of sets. When we started this video, we talked about several intuitive cases where we felt like we knew what the limit should be, and we put lim in quotes. Let's go back to them. The first one I want to look at is a decreasing sequence of sets, A1, A2, A3, like this, wrapping around some intersection, which could be the empty set. I don't know. Remember, we said that the quote unquote limit of this sequence of sets is going to be the intersection of all of the sets. But now we have a definition which says we have to look at the Limsup and the Liminf, and if they're the same, that's how we define the limit. So let's start with the Limsup. It is an intersection as n goes from 1 to infinity of a union as m goes from n to infinity of the am. So let's consider this set over here. When m is 1, we're unioning all of these sets. And because we have this decreasing sequence, the union of all of these circles that you're seeing here is just the biggest circle, the biggest set, A1. And if you union them as m goes from 2 to infinity after chopping off the first set, you're going to get this second circle. And this second circle is the set A2. In other words, the union as m goes from n to infinity of am is just an. Right? So the union from 1 to infinity is A1, the union from 2 to infinity is A2, the union from 3 to infinity is A3, and in general, the union from n to infinity is an, so that's what I'm going to write right here. And look what we have. The Limsup of this sequence is an intersection of sets, and there's not much more I can say without knowing anything about these specific sets, but this is how we define the limit of the whole sequence. And it now turns out to be what the Limsup is given the definition of a Limsup. So we are halfway there to showing that the limit of this decreasing sequence is the intersection. We need to look at the Liminf. The Liminf of the sequence of sets is the union as n goes from 1 to infinity of the intersection as m goes from n to infinity of the am. Let's consider this intersection when n equals 1. It's the intersection of all of these sets, which appears in this picture. It doesn't have to be something down here in the core. And if we intersect from A2 on down, that also appears to be the same thing. In fact, the intersection from 1 to infinity is the same as the intersection from 2 to infinity is the same as the intersection from 3 to infinity, and so on. So the value of n here is irrelevant. As a union, we're unioning things that are constant in n. Like what if someone gave you a single set A and asked you to union it with itself n times? You're still just going to get A. So if I union the same set over and over again, I'm just going to get that common set. Again, that is the intersection as m goes from 1 to infinity of the am, or in this case, I decided to write it with an n. Hopefully there's no confusion there. It's an index. It's kind of weird to say n is going to infinity and then have n on the right-hand side. So maybe I shouldn't have done that, but technically it's okay. It's describing an intersection. You can use any index you want. The point is we got the intersection of all the sets when we computed the Liminf, and that's the same thing we got when we computed the Limsup. Since they're the same, we say the limit of the sequence exists, and we define, no more quotes, we define the limit in n of the an as a, where a is defined to be the intersection of all of the sets. And we again would write a with a southeast pointing arrow down to the set A. I'm going to leave it to you to do the other direction. So start with an increasing sequence of sets, A1, A2, A3. And we thought in the intuitive part of the lecture that the limit there was going to be the union. So if you find the Limsup and Liminf by the definitions with unions and intersections, you should be able to show, it should be quite easy to show that the Limsup is equal to the Liminf is equal to the union of all of the A's, which is what we had back on the slide where we were talking about this more intuitively. So again, I'm going to leave the other direction for these subsets to you. Let's reconsider our third, which was actually our first intuitive example, where our space was real numbers and our sets an were the intervals from 0 to 1 minus 1 over n plus 1 closed on both sides. So this is a sequence of sets that is increasing. So I already know that the limit exists and is going to equal the intersection of all of these if we use what we previously talked about for increasing sets. But let's say we can't remember that and we want to go straight to the definition of Limsup and Liminf. Let's just try it one more time. The Limsup of this sequence is the intersection as n goes from 1 to infinity of the union as m goes from n to infinity of the am. I want to consider this term when n equals 1, when n equals 2, when n equals 3, So if I union all of these, I get the interval from 0 closed to 1 open. And I get that when n is 1 or 2 or 3, I always get the same answer. So I am intersecting a bunch of equal sets. Like if you have a set called A intersect A, intersect A, intersect A is just A. Nothing's happening with the intersection. In other words, the lim sup here is just that intersection, which is the interval 0 to 1 closed on the left and open on the right. For the lim_inf, recall that the lim_inf is defined as a union as n goes from 1 to infinity of an intersection as m goes from n to infinity. And again, I want to look at these intersections for various values of n. So when n is 1, I am intersecting all of these intervals. And because of the containment, it's easy to see that the intersection is just going to be this first set. So 0 to 1/2 closed on both sides. And now if I take off the first set and intersect the rest of them, I am getting the set A2 because the intervals are increasing, right? And if I want to intersect them, I get the smallest interval because they are nested. So the intersection, when I plug in n equals 2 to this, is the interval from 0 to 2/3 closed on both sides. And the intersection, if I cut off the first two sets, is so we get A1, A2, and A3, and A4 out of the intersection of all of them -1, all of them -2, and so on. So we actually have something to union here. The lim_inf is going to be the union as n goes from 1 to infinity of an, because each of these intersections is just one of the a's. But if you look up here at these sets and union them, you're just going to get the whole interval from 0 to 1 closed on the left and open on the right. The same thing we got when we took the lim sup, which means the limit exists, and we no longer need to use quotes around it. The limit of these sets is equal to the interval from 0 to 1 closed on the left and open on the right. Let's look at one more example, a kind of goofy example. Let's return to our coin tossing experiment where we flip a coin 3 times and we have a sample space consisting of 8 outcomes, heads, 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 tails, etc., all the way down to tails, tails, tails. Now, I am hard pressed. I could probably do something, but it would be very messy. I'm hard pressed to come up with a sequence of sets that I can index by n. So I'm just going to do something kind of goofy. I'm going to let an be the set heads, 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 tails, 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 heads whenever n is odd. And I'm going to let it be the set tails, tails, heads, tails, tails, tails whenever n is even. Not only is this a goofy example, but it's really just an example of a sequence where you're alternating two constant sets. So the coin flipping is not important here. Let's just say, to make this easier to talk about, that an is defined to be some set b when n is odd and some set c when n is even. You just get the sets alternating. So it seems like a limit wouldn't exist unless maybe b and c were the same. But let's see what we get from our definitions. I definitely don't have containment here. Like if b happens to be contained in c, then that's not contained in b. And we don't have an increasing or decreasing sequence necessarily in general. But the lim sup is the intersection of the union of the AMs. Now, if I union any number of these A's, I'm going to get B union with C, union with B, union with C, or maybe I start with C, union with B, union with C, union with B. But ultimately, I'm just going to collect the two sets and have B unioned with C. And this set does not depend on n. So I have yet another case of an intersection of a set with itself again and again and again. And that's going to give us that set, which is B union C. As for the lim_inf, I'm going to write out the definition, and I'm going to start by looking at this intersection. So what is the intersection of all of the sets? It's just the intersection of B and C. Yeah, it's B and C and B and C and B. And intersecting all of them is the same as intersecting just B and C. And if I cut off the first one, I'm intersecting C and B and C and B. And that intersection is still B intersects C. So this intersection is unchanged no matter how many I cut off. The intersection part is always going to be B intersected with C. So I have the union as n goes from 1 to infinity of a set with itself and itself and itself. And the union is just going to be B intersects C. This is not the same as B union C in general. It could be if B and C are the same. So in general, the limit of this sequence is not going to exist. And when will it exist? It will exist when B equals C, which is a very boring limit, like B, 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 B. Next up, complements. Let's look at the lim sup of a sequence of sets. Now we know this is itself another set, and because it's formed with intersections and unions of sets. And so this set has a complement. To compute the complement, I'm going to write out the definition of the lim sup as an intersection of a union. Recall De Morgan's laws. Like if you have a union of two sets and you complement the whole thing, you get the first set complement intersected with the second set. And if you have the intersection of two sets and you complement the whole thing, you get the first set complement unioned with the second set complement. I think I forgot to say the other complement, but you know what I mean. So I am going to distribute this complement through this intersection, and that is going to turn it into a union and put a complement on each individual set from that original intersection. And now I'm going to distribute the complement through this union, which is going to flip this union to an intersection and put the complement on each set. So again, this is De Morgan's laws. But now this is our very definition of the Liminf of not the AN set, but AN complement, because I'm not looking at the original sets here. I'm looking at the complements. So if we take the complement of the lim sup set, we get the same thing as the Liminf of looking at the complements to begin with, and vice versa. You can imagine this going the other way quite easily. You have a Liminf and you're taking the complement of that set, you'll end up with the lim sup of the individual complemented sets. Okay, so before wrapping this up, I just want to do a little bit in terms of language and notation. Let's take a point omega in the lim sup set. That means that it's in this intersection of this union. Now, if it's in the intersection, as n goes from 1 to infinity, it needs to be in this union from n to infinity for all n, when n equals 1, when n equals 2, when n equals 3. But at each stage, we're chopping off another a, and it's always in there. And that means that the omega is necessarily in infinitely many of the ans. And if you go back to the beginning of this course where we thought of sets as events from experiments involving probability, like you flip the coin 3 times and you let A be the event, you get at least 1 heads, something like that, then the lim sup set is also a set that could be thought of as an event. And it's kind of like the event that infinitely many of the AN events happen. So notation that is used, the lim sup set is often written as this with these square brackets where we write ANIO, and the IO stands for infinitely often. Some people will use curly brackets and some people will use no brackets at all. But if you see ANIO, as weird as that looks, it's just referring to a set, and that set is the lim sup. On the other hand, if we take an omega in the Liminf, that means it's in the union of this intersection. Now, if it's in this union, it has to be in at least one of the intersections. So it's got to be in the intersection, and as m goes from n to infinity for at least one n. Now, we're intersecting an infinite number of sets in any case, no matter how many we cut off. So it's got to be in all of the sets, except for maybe some at the beginning. We say that omega is in all but finitely many of the AN. So the event that the Liminf event happens is means that the outcome from our experiment is in all but finitely many of the sets or events. And sometimes this is written as AN eventually, but this is pretty rare terminology. The ANIO you'll see all over the place in measure theory books, but you won't really see this one very much at all. But there it is for the record. Throughout this whole video, I didn't talk about the measurable space. I just was talking about unions and intersections, but presumably we're starting with a measure space consisting of a non-empty set omega, a sigma field F, and a measure, which will likely be a probability measure, so I'll call it P. If we take a sequence of sets from the sigma field, the lim sup and the Liminf as unions and intersections, countable unions and countable intersections will still be in F because sigma fields are closed under countable unions and countable intersections. And remember, F is the collection of sets on which we've defined the probability measure. So it will make sense for us to talk about the probability of the lim sup happening. The probability of the lim sup is just another set. So the probability that an outcome in that set happened and the probability that we had an outcome in the Lim-Inf set. Again, if these sets come from a sigma field, these unions and intersections are still in the sigma field. The Limsup and the Liminf are just new sets still in the sigma field, and the sigma field is where we define P, so it does make sense to talk about P, the probability of these events occurring. And of course, if they are equal, then the limit set, the limit of the ANs is just another set in F, and F is where we defined our measure P. So it does make sense to talk about P of the limit of the sets. I have a question for you. How do you think this relates, if it does, to the limit of P of the sets? So here I've got the probability measure of a set. And here I've got probability measures of a lot of sets. And this is a sequence of real numbers that I can take the limit of. So taking the limit of the sets and plugging it into the probability measure, or measuring each set and taking the limit of those numbers, do you think they relate? To find out, you're going to have to come back. Next time, we're going to be discussing what is known as continuity of probabilities, and we're going to see that these do relate and are sometimes equal, sometimes not. And I'm a little excited, so I'm going to tell you what's coming after that. We're getting to the famed Borel-Cantelli lemmas. So I hope to see you in the next one.